All right, hey everyone, welcome to Multimodal Weekly. This is a webinar series hosted by 12 Labs. We are a startup Series A company focusing on building multimodal foundation models for video understanding. This is the initiatives that focus on, I guess like enabling the technical community, researchers and developers to learn more about the exciting field of, multimodal AI and foundation models. We've been meeting on a weekly basis over the past 2 years or so. Typically, we tend to cover different wide variety of ranging projects, from the research side to the application side to the I guess startup partnerships, industry focus as well. These are examples of recent talks on our session. Interesting research that focus on Google modeling, benchmarking, video editing, broadly speaking, multimodal learning. And for today's session, we have two pretty exciting presentation, and they both focus on the very exciting booming space of reasoning models. The first speaker will be Shao, will also go by Ray, and then we'll have Rulin and Co here as well. But they've been working on a project called ReasonIR, and this is the first retriever model specifically trained for general reasoning tasks. And it achieves state-of-the-art retrieval performance on the Bright benchmark, which is specifically focused on reasoning intensive retrieval. And then the second presentation will come from Zhen Zhang. He will talk about his work called soft thinking, which is a training-free method that emulates human-like soft reasoning by generating soft abstract concept tokens in a continuous concept space. So yeah, I'm pretty excited to, I'm intrigued to hear more about this concept of concept space, and Zhen will walk you in details in the latter half of the webinar. Just a note on the logistic for the attendees. Feel free to send your question on the Zoom chat, and I can bring it up async to the speakers. And then after each speaker finish, we'll have a short Q&A, so you can be interactive and answer question in real time. With that, I will stop sharing my screen. And yeah, Ray, do you want to go ahead and start your presentation?
Okay, yeah, thanks, James, for the introduction. I will start sharing my screen. Just a minute. Can you see my screen?
Yep, we'll see it.
Okay. Okay, yeah, thanks, James, for the introduction. Rulin and I are very honored to be invited to be the speaker in this weekly webinar organized by 12 Labs. So today, Rulin and I will be presenting about ReasonIR, training retrievers for reasoning tasks. Sorry, I probably need to edit a bit for the video on the side. Just a moment. Okay, it all works now. Okay, so for ReasonIR, this is a joint work that is done between Faraday Meta, UW, NUS, Smart, AI2, and many other organizations. So a bit of a background. Retrieval-augmented generation has been widely applied in knowledge-seeking tasks, such as factual question answering. It's mostly used for retrieving factual knowledge to understand or answer the query. However, it is often unclear how RAG can be helpful for reasoning-intensive tasks, such as math, coding, logic, and other STEM subjects. And how are those tasks different from the traditional knowledge-seeking tasks in terms of retrieval? So here comes to a comparison between factual retrieval and reasoning retrieval. In traditional factual retrieval, the query are usually simple, and the query can be matched to relevant documents via simple keyword matching or semantic matching. So in this example, the two documents could be easily matched to each other via the keyword Yellowstone National Park. However, for reasoning retrieval, it is much more complicated. So the two documents seems to have non-overlapping keywords on the surface. However, they are relevant to each other because both of the documents can be solved or analyzed via this pigeonhole principle. So this is what we call reasoning matching, and it is much more difficult compared to a factual retrieval. Another example is in this stack exchange problem. A user asks, how good is it to reuse the water from plant pots? So to answer this question, we need to understand that soluble salts are commonly found in soils, and reusing the water to water the plant pots will cause accumulation of soluble salts, which could be bad for the growth of the plants. And this is an actual helpful document, which is shown on the bottom right of the screen. However, if we use the traditional factual retrieval based on keywords or semantic matching, we might end up with getting documents such as water garden or aquatic garden, blogs related to self-watering pots, and water reuse can provide alternatives to existing water supplies. These appear relevant, but ultimately unhelpful documents. So what are some of the potential helpful information for reasoning tasks? This includes prerequisite knowledge that contains preliminaries, tutorials that present effective reasoning patterns, demonstration questions solved using similar methodologies, and also underlying principles and concepts that are crucial for the analysis or answer. Can current retrievers find this information? Unfortunately, the answer is no. In particular, in prior work called Bright, which is also the main benchmark we use to evaluate our model, it covers 12 domains across different subjects, including biology, economics, coding, and math. So these are much more complicated than the traditional keyword-based or semantic-based retrieval. In the original paper of Bright, they show that the performance of the existing retrievers on these reasoning retrievals are often limited. So in this figure, when evaluated using a metric called NDCG at 10, which evaluates the ranking quality of the top 10 documents retrieved by the retriever, we can see that the performance are somewhat disappointing, where the NDCG 10 score could go up to 100. And they perform poorly on these tasks. And so the research question we want to deal with in this talk is, for reasoning tasks, if we only retrieve once, what information is helpful and how to search? We break down this talk into 3 components, covering test time techniques, including query writing and document re-ranking. And second component is retriever, which is also the main contribution of this work, where we obtained ReasonIR AB using data synthesis. And also a bit about the data store we use, including MassiveDS and CompactDS. So before training the retrievers, let's first revisit if test time techniques can solve the problem of reasoning retrieval. We'll be discussing 3 different types of test time techniques, including query decomposition, rewriting, and LLM re-ranking. So first, let's look at query decomposition. We use implementation provided by LongChain, which breaks a complex query or a reasoning query into short and simple queries. So, but if you look at the performance, after the query decomposition, although some test time compute has been spent, the performance degrees compared to original query for both retrievers, including Nomic and Grid 7b. And this tells us that a naively decomposing a reasoning-intensive query might not always work. And a second technique we investigate is query writing, which augments a query with chain-of-thought query writing from a larger language model. This could potentially include richer information into the query. This prompt was used by the original Bright dataset, but we controlled the output length via a max token prompt. So if we look at the figure on the right, and the x-axis shows the length of the COT rewritten query, and the y-axis shows the retrieval performance on Bright. If you only look at the bottom 3 curves in gray, pink, and green colors, we can see that the performance quickly saturates or even degrades as the reason query length increases. So this tells us that the length of query can be a new scaling dimension because it initially increases, but current retrievers cannot effectively leverage it. And in addition, the third type of test time technique is LM re-ranking. So we can simply ask LM to give a relevant score between 1 and 5 and re-rank perhaps the top 100 retrieved documents from the retriever. And if we look at the performance generally increased a little bit, but it is still unsatisfying because it is so far from achieving 100 of NDCG at 10. So the conclusion is that re-ranking on existing retrievers does not significantly improve at the expense of more test time compute. So while test time techniques don't work well with existing retrievers, we want to train a better retriever that is not only good itself, but also good at leveraging the test time techniques. And this is the main message from ReasonIR. So in order to train a retriever for reasoning tasks, we like to look at the training data. So existing retrievers are mostly trained on public training data for factual retrieval. And most of the data consists of simple queries and positive documents, which could be matched via keyword matching or semantic matching. And these public data has two properties. So first, they focus on factual question answering. So the resulting retrievers are usually good at semantic matching, but bad at reasoning intensive retrieval. And the second property of this data is that these queries are usually direct and short, which results in the short effective context length. And we can see that from the previous scaling analysis, and most of the performance of the retriever quickly saturates as the length of the rewritten query increases. So we would like to address these two issues. So the first type of data we propose in the ReasonIR data is to increase the effective query length. So we would like to generate synthetic data with varied length. So in this case, we synthesize everything from scratch using a large language model. And in this case is Llama 3.170B. So we synthesize the varied length query of different lengths from short to long. And then we synthesize positive documents based on this query. And we also synthesize the hard negative documents based on the query and the positive documents. And this is because usually when training the retriever, the hard negative documents are very important in terms of performance. And we find that if we simply use BM25, the performance is not so satisfying. And the second type of data we generate is the hard query synthetic data. And the objective is to increase the difficulty of the query. So the procedure works as follows. We start from initial documents of STEM subjects, and then we filter these documents using FineWeb-edu classifier, and only the high scored documents were kept as seed documents. Then based on these documents, we use a large language model to generate the hard queries. So these queries are typically reasoning intensive and requires a lot of analysis compared to the existing factual questions. And then we also follow the same procedure as before. We generate the hard negative documents based on hard query and the positive documents. So if you look at these two types of data, the length of these two data are much longer than the existing public training data. And the difficulty is also much higher, where we evaluate the difficulty based on the error rate of some of the existing retrievers. And this is an overview of all the data that we use to train the retriever, consisting of the existing public data, the varied length data, and hard query data. We train our retriever using contrastive learning with in-batch and hard negatives. It is also trained based on Llama 3.1AB. So as a result, let's look at some of the experiments. So its effective query length increased. If you look at the performance of our model on top of the curve, it shows a much better scaling trend compared to existing retrievers. And is the retriever better at handling hard queries and longer length? If you look at the performance chart below, So on the first block, we evaluate the retrieval performance on original reasoning-intensive query. And our model outperforms all existing baselines. And if you look at the second block, when it's evaluated with GPT reason query, which means the original query has been rewritten by a GPT-4 with a much longer context, our model also outperformed existing approaches. It is also capable of generating a hybrid prediction when it's combined with BM25 and obtaining much better performance. How does it work with LLM re-rankers? So we also develop this ReasonIR re-rank, which is a simple yet effective LLM re-ranking method with a tie-breaking technique. So what we do is simply ask LLM to give a score between 1 and 5. And then because these scores are discrete, we like to break ties by interpolating the LLM re-ranking scores with the base retriever scores. And if we look at the performance on the right, we can see that after applying this re-ranker, the performance goes up 7 points, which is extremely significant compared to previous re-ranking methods. And another benefit of having ReasonIR is that if you look at performance in the middle, it is 200 times cheaper than existing best re-ranking based method. And it also outperforms these approaches. How does it generalize to reg tasks? So we don't want to just be able to retrieve relevant information. We also want to test whether these things are really helpful in downstream tasks. So we apply the reader, which is a Llama 8B or Qwen7B instruct. We also use the data store MassiveDS, and we evaluate the record performance on MMLU and GPQA datasets. And we can see that when using ReasonIR to retrieve documents from MassiveDS data store, the performance outperformed existing approaches, and even for the search engine. As an evaluation study, we would like to also understand the composition of data of the training set. So in this chart, we can see that for any of the synthetic data that's removed from the training data, the performance can go down significantly. We also studied the performance of an easy query, which is generated based on the same set of seed documents as the hard queries, but performance also degrades. This shows that even though the seed documents share the same distribution, it is often crucial to generate hard queries compared to just simply generating easy queries. In this experiment, we show that there is a lot of space of improvement with an oracle ranker. And what this chart means is that after retrieving the top 100 documents, we assume there's access to the oracle ranker. And oracle performance can go up to 71.8, which is a very significant gap compared to the existing performance, which is only about 30 plus. And this shows that there is a big gap between the existing re-ranker and oracle re-ranker. In addition, ReasonIR 8B also has a much higher recall at 100, showing that it is retrieving much more relevant documents compared to other existing retrievers. And some of the limitations, synthetic data is playing a crucial role in enhancing the performance on complex tasks. However, we did not explore the scaling behaviors of the size and difficulty of such synthetic data for embedding training. And another way to collect challenging training data is to crawl the web and collect human annotated data. We did not explore this direction due to the lack of automated crawling tools and good quality filters. And in addition, we only consider the single-turn retrieval. We did not consider multi-turn retrieval. We hypothesized that improvements on single-turn retrieval can potentially translate to more improvements on multi-turn retrieval. We encourage developing retrievers that explore more possibilities of potential helpful information beyond semantic matching, aligning with reset laws defining that reasoning tasks attribute to a broader range of knowledge. So what this figure shows is that for factual queries, it's often easy to find the relevant documents from the data store. But for reasoning queries, the relevant documents are much more distributed. So many of the existing documents could be helpful. So it's much harder to find those compared to the factual queries. We have improved the retriever And what about the data store? So in the next section, we'll be talking a little bit about the data store used when evaluating other RAG tasks. So it is often crucial to make sure the helpful information exists in the data store. And MassiveDS is an awesome data store, and is also the largest open source data store that covers a broad spectrum of domains. So the reason why MassiveDS data store is really good is because of its size and diversity. In terms, so we can see that MassiveDS improves the general downstream tasks, and it often shows a better scaling behavior as we increase the size of the data store. And in addition, having diverse domain in terms for the data store outperforms single domain data store. That's also the reason why MassiveDS can outperform existing data stores, which are often single domain on all of these tasks. It is also very easy to use. You can simply do pip install and start a server using a single line serving support. And in addition, a more compact version of MassiveDS called CompactDS has also been released, which will also be supported in MassiveServe. The paper has been released and the data store has also been released. So if you have more questions regarding this, you could ask Rulin about it. Yeah, thanks for listening to the talk. Any questions?
Awesome. Yeah, thanks, Ray, for walking over the details of the paper and explaining the key experiment and the architecture as well as the results. So yeah, there's actually one question from Suvaris in the chat. Yeah, so do you want to take that? Either you or Rulin could take that. Just feel free to unmute yourself, by the way, so you can answer it.
Yeah, sure. I can take the question. Do you want to explain a bit more about like how you do reasoning over knowledge graph, or do you mean retrieval over knowledge graph using our retriever?
Yeah, Suvasis, I think that's one for you. If you can just unmute and explain your question. I think he got a follow-up point. Like he said, his data is high frequency nanosecond data for stocks. He wanted reasoning on this retrieval. So maybe that's the context of his question.
Oh, gotcha. So I think for current RAG, we usually flatten the data to perform a fast retrieval. So if you have special data, there are some related work on graph retrieval, so where you can perform more structure retrieval by iterating through graph or like hierarchical retrieval. So I don't think you can directly apply what we have done in this work to that data. But I think for reasoning parts, it's universal that you can consider adding query writing, this test time scaling techniques to augment your query information and then perform retrieval on the data. So I think the change will be more done on the index structure set. So you need to figure out what's the specific design of the data and then modify the data store implementation correspondingly. So I think for reasoning part, it should be transferable. Does that answer your question?
But yeah, just maybe to add up a bit, because it looks like this type of data is also slightly different as it's high frequency nanosecond data. So maybe this is also a different type of data that we synthesize during the data generation process. So some of the ideas from our work in terms of data generation might be borrowed, or you can perhaps, given your existing data, you could synthesize some of the data and then train a retriever based on these data, which could be helpful as well.
Perfect. Great. Maybe one question from my end is future direction for this work. I briefly going over like the archive page, and I think you have one session towards the end where you talk about different direction for this work, right? Everything ranging from studying the scaling trends of synthetic data, extending it to multilingual and multimodal versions, and then combining it with multi-turn reasoning models. Can you share a bit more details on that front? Especially work around like multilingual and multimodal. How can this retrieval, be appropriate for, additional modalities or like, new languages? Yeah. Do you want to answer that question?
I really do want to share a bit more.
Rulin?
Oh, well, maybe if she's not here, I can do something first. Yeah. So I think the reason why we mentioned the multi-term retrieval in this case is because of the potential application in deep research. So usually a user will be asking a simple, uh, not simple, but like a complex question in a very simple manner. And then like in order to answer this question, the model needs to retrieve for multiple times. It needs to examine the documents that has retrieved at this stage and do some further analysis, and then maybe retrieve again if more information is needed. So across this process, we can see that there are two things the reasoning might be helpful over here. So the first one is explicitly trained for reasoning tasks. And throughout the process, all the different kinds of queries that the model is addressing requires extensive reasoning. And secondly, you can see that the context length keeps growing over time because the more documents the model retrieve and the more analysis it's done or the more summary it generates to answer the query, the length of the context keep increasing. So in this case, it is also crucial to have a retriever that could work with a long context. But of course, there's also a limitation here. We only do the longer context for the single term retrieval. It's potentially helpful to keep increasing the effective context length of the retriever specifically catered for this multi-term retrieval. Yeah, so that's my understanding for this multi-term retrieval. Rulin, do you want to add anything?
Yeah, so when I add the slides, I was also thinking about more recent application about deep research stuff. So where you ask the LM to do interleaved reasoning and retrieval, and at each step, the model needs to seek for new information based on its past reasoning context. And it's still quite important to make sure you can still reach what the model is asking for. For example, when you are handling a math problem and ask for is there any algorithm can help solve this? So if your retriever can directly reach that particular algorithm without the model speaking out the exact name, then that would be super helpful and I can also save the number of turns of your model to perform reasoning. So I think the number of the capability of the model to conduct multi-turn reasoning and the capability of the retriever to perform high quality like search are both important to achieve like next level of RAG applications like deep research. So we leave the multi-turn part as a future work.
Awesome. Yeah, thanks for answering that question. Yeah, I just had to, see some of the future work and upcoming improvement for multi-turn, multilingual, multimodal initiatives. So I know we passed, the first half hour of the webinar. So I would like to, thanks Ray and Rulin for presenting ReasonIR and answering some of the audience question. If there are more questions from the audience, feel free to continue it, put it on the chat, or you can reach out to the speaker after the webinar ends. With that, I want to let the second speaker, Zhen, to if you want to start sharing your screen and go ahead with your work on self-thinking.
Can you see my screen?
Yes, monsieur.
Yeah, okay. Thanks, James, for the invitation. So today I'm going to introduce our recent paper called Self-Thinking, Unlocking the Reasoning Potential of Large Language Models in Continuous Concept Space. And yeah. So I will first introduce the background and introduce our method, and then do some theoretical explanation and give out our results. And I will do some conclusion and introduce our future work. Yeah, and the soft thinking is a joint work between UC Santa Barbara, UC Santa Cruz, Zhen team, and Microsoft. And then, so yeah, as we all know, that chain of thought is a reasoning technique where the models can generate step-by-step intermediate reasoning steps in natural language. For example, when you solve a problem, when you count, for example, the question of the answer of this question, you can for the standard propping, you directly give out the answer. For here is 27, but for the chain of thought, you can do step-by-step reasoning. You can first solve the step A and solve the step B, and then finally you give the correct answer 9 here. Yeah, but the chain of thought have some limitations. Yeah, the first is the reasoning step is sequential. You must first solve step A and then do the step B. You cannot do parallel thinking here. And then the second limitation is that the chain of thought relies on discrete tokens and the human language, and which limits its ability to represent abstract or fluid concepts. But human think in parallel. For example, you can think of A and B together, and then you will find A is better, and then you will continue to think more about A. And humans think are more abstract and continuous instead of just discrete tokens like a word or some sentence. People think in a very abstract and with some concept. Yeah, so and then let me introduce our soft thinking method. In this paper, we propose soft thinking. It's a training-free method that can enable reasoning in continuous space. So what we do is that we replace the discrete token sampling with concept tokens, which preserve the full probability distribution and enable large language models to think abstractly and in parallel. And for the result, the soft thinking simultaneously improves both accuracy and efficiency across reasoning tasks like math and coding. Yeah, and then let me introduce the method of soft thinking step by step. So in the first step, the input is the same as soft thinking. It's the same as chain of thought. For example, you have a math question or the code question. You just decode the question to discrete tokens, just the same as chain of thought. And then the second step is very different. So for chain of thought, when you calculate the distribution, the probability after softmax, you do sampling, and then you select just one token at each step. But for soft thinking, we keep the full probability distribution. We do not do sampling. We just give this full probability distribution to next step. And here we can see the CT1 here. This is the input token for next step. And then after we get the token for next step, we need to calculate the embedding for next step. So we just use a weighted mixture of all token embeddings here. We multiply the probability of each token and with the embedding of each token and sum them together to get the embedding of next step. And then we just repeat the step 2 and 3 until the highest probability of concept token is the end of thinking token. And then we just generate the output with the discrete token, just go back to the chain of thought instead of soft thinking. Yeah, and then here is the method is good, but we encounter some problems. For example, well, the concept tokens enable more abstract reasoning, but the concept tokens can lead to a generation collapse because during the pre-training or post-training stage, the large language model did not see that kind of tokens. They just know how to understand discrete tokens, but they don't know what is these continuous tokens. So this is out of distribution problem. The model will sometimes cannot stop generation. So we need a method to stop the repetition and then let the model give out the answer so that we can the human can understand or our code can understand what is the answer of that simple. So we propose the code stop method. It dynamically stop thinking before the generation collapse. So the method is very simple. We just monitor the entropy of each concept tokens, and the entropy is just calculated by the p times log p, and then we sum them together. And then when we find the entropy stays low for k steps, the soft thinking, we just let the soft thinking to conclude. We just concat the end of think token to the end, and then let model to give out the answer. And here are two hyperparameters. The first is the threshold of entropy, and the second is the k here. So how many steps after that we need to stop soft thinking. And in practice, the entropy here we select for 0.1, and for key here we use 200 here. And then here are some theoretical explanation for the soft thinking. Here we just did some a linear approximation of next token prediction process. Yeah, firstly, we began by considering the general problem of predicting an entire sequence or answer, denoted as y here, and given an initial input x. And then this is represented by the probability y given x. And then we can decompose this probability as shown in the equation 8. We can break down this prediction by focusing on the first token the large language model generated, which we call the T1 here. And we can express the overall probability Pyx as a summation over all possible token in the vocabulary for T1. And the formula is the summation of P Ty given X times Py given X and T1. And so in this term, we are averaging the probability of getting the final answer y over every possible first step. And then we need to go back to the definition of concept token. Is how do we represent the model's initial idea of what to generate next? We define the first concept token labeled CT1 as the expectation of the first token T1. As you can see in the equation 9, we treat T1 as the one hot vector, and its expectation is the probability of T1 times the embedding of T1, and then it just gave out the distribution, the probability distribution of T1. And this is simply the definition we gave out of the concept token before. Yeah, and then by sorry. Yeah, and then by this linear approximation of P y given x, and then we can just do a linear approximation. For example, we can put this probability P here to the inside, and then we get the P T1x times T1 here. And then we can just replace this term as the concept token we defined before. So here the full summation is replaced by just a single evaluation at the concept token T1 here. And after we get the approximation of P y given x at the first step, we can do it recursively. We can then replace it with CT2 here, and then CT3, CT4 until at the end of token appear. For example, here we got the CTM at last. So the PYX, a PY given X, CT1, CT2 until CTM is a linear approximation of the original P1 given X. Yeah, and here are some insights for why the soft thinking works and why we propose the soft thinking. And in our experiments, we find that as the model's capability improve, the number of tokens required to do generation will also decrease. For example, you can see the figure at the bottom right. The model size increased from 7 billion to 32 billion, and the model is the DeepSeek Distill Queen, and the dataset is AIME 2024. And as we can see for the orange orange line, this is the token we need, and we can see the number of tokens just decrease as the model size increase, but the performance, the accuracy just increase. So as we can see, the efficiency and the effectiveness is not a trade-off as the model size, or we can see as the capability or the ability of the model increase. So the soft thinking just make the large language model or the reasoning model more powerful, so they can increase the efficiency and effectiveness simultaneously. And then why soft thinking need less token compared with chain of thought? Because at each step we just preserve the full distribution of a full probability distribution of each step, so it contains more information in one token. Therefore, for the whole reasoning path, the large language model just need less token for generation. And then here are some results for the soft thinking. The first is an example of the full distribution, and we just select the top 3 tokens here. And as we can see, the model can represent nuance in between concepts that are not captured by any single word. For example, in the first line, we can see that the model search for several reasoning paths. For example, the first line is I will start, and the second line is I can break, and the third line is I use. This is like the model are searching for which path it will use. And for the second line on the right part, you can see that the model are thinking what they will first do for the calculation. For example, at the 32 steps here, start from 32, the model output 4 and 3, and they will do the multiplication, and they will choose to multiply by 4 or 30 here. But after they calculate the probability, they find that the 4 have higher probability. So then they just conclude they will multiply 43 by 4 here, and then they just give out the answer 172. And then you can find that after they conclude this path, the distribution will just limited to the top 1 token afterwards, and there is no other parallel reasoning path after he has concluded the reasoning path. And then we also have some example of shorter reasoning paths. As we can see, the model knows just decompose the reasoning paths 34 into 30 and 4. They do it in parallel, so they don't need the first sentence in right here. And then they just calculate the multiplication parallel, so they don't need to explicitly give out how they compute the 43 by 30. So the soft thinking did not use the second right sentence in child soft thinking. And then here are some experimental results. Do experiments on 3 models. The first is QW 32 billion, and then the DeepSeek R1 distill Kun 32 billion, and Llama 70 billion. As we can see, the soft thinking simultaneously increased the accuracy of the result. For example, it increased the accuracy up to 2.48 points, and also they decreased the generation length, and the result is the same as we do on the coding tasks. The model increased the accuracy up to 0.9, and the generation length decreased by 20%. Yeah, and here are some takeaways and future work of soft thinking. I think the soft thinking allows just a large language model or even the reasoning model to reason in an abstract and parallel manner, and it achieves simultaneous improvement in accuracy and efficiency without any tuning. And also we can see that the result is very readable and interpretable, and it's very practical for real-world applications. So for the future work, I think we can explore, because this is a training-free method, and it have some out of distribution problems. So we can explore training model on the concept tokens to enhance robustness and generalization. And also we can extend soft thinking to multimodal reasoning. For example, we just replace the text input with the image input. And then we can also do the parallel abstract reasoning with soft thinking. Yeah, so that's all for my presentation. Do you have any questions?
Awesome. Thanks, Zhen. I don't see any question yet on the chat. So yeah, attendees, if you have any question, feel free to put and you know ask them right away. Maybe one question from my end in terms of like future direction. So you mentioned that one of the future work is integrating training-based approach to adapt the concept token.
Yeah, so because this is a training-free method, so we found that because of the model did not see this concept token before, so it sometimes cannot stop the repetition. So maybe we can, for example, do some reinforcement learning for the concept token. They will learn the for the next step, what kind of distribution we will generate for doing soft thinking.
And then the second part about extend soft thinking into multimodal reasoning. Can you elaborate more on that? How does it gonna work with like say image or video, you know?
Yeah, sure. So I think for soft thinking, we don't care about too many about the input. For example, for the reasoning, multimodal reasoning, for example, for the lava, the input part we just encode the image to the by clip model and then to an embedding. But this is for the input part, right? So whatever the input, for the soft thinking, the input is the same as chain thought. So the soft thinking is just replace the decoding part or the output part of chain of thought. So we can easily apply soft thinking to multimodal reasoning, and I think we don't even need some training. We just this is a plug-in method for multimodal reasoning, but we actually did not do any experiments in this paper, and we think, but I think we can easily apply soft thinking to some multimodal models.
Okay. I guess final question is, everyone in the field know about chain of thought reasoning. Looks like, it's a very popular method. And how do you think, people can adapt soft thinking for like real world application? How do you think, more people can be aware of this approach?
Yeah, I think so actually I think that we can just directly replace the chain of thought reasoning with the soft thinking. But the most important part is that for the thinking part, because for chain of thought we have input and then the thinking and then the output. But for the thinking part, we have many, we just keep the full distribution of thinking. So we need to store the whole distribution. But if the reasoning paths have, for example, 10,000 tokens, we need to store too many things, too many tokens for just one question. So maybe we need to select top K or just top 3 tokens for reasoning to improve the efficiency, the store efficiency.
Great. Well, awesome. Thanks, Anne. I think I'm really super excited about that. I think multimodal having, seen a lot of work that apply reasoning concept yet. So some of these idea from like reasoning that we can bring over from language model to the multimodal side, I think could be super cool, right? Imagine if we can build like a image reasoning model or video reasoning model, right? I think which is kind of what we think about here at 12 Labs. So yeah, I started to see more this adoption of these new novel techniques, and yeah, I know your lab is also doing pretty cool work, right? On this research direction. So excited to see more papers coming from yourself and your colleagues that tackle this issue. Yeah. So I know we're out of time, so appreciate Zhen for wrapping up the webinar on the second half, and thanks the attendee as well for watching and asking questions. The recording of this session should be available on YouTube probably by early next week. So be sure to share that link with the speaker, and they can promote that with their colleagues. And if you have any for the attendees, you have any question follow up from this session, you can you have to email the speakers. You can follow up with more details. For folks who will be watching this session async after the fact, you can also reach out to folks. I'll be sure to include all the information of the papers and the speaker in the description as well. And yeah, thanks everyone. Appreciate your time, and hope you have a good rest of your weekend. Bye.
Thank you.
Thank you.